In this lecture, we will learn what are the multiple integrals and how do we use them. So before actually defining the multiple integrals, let us first revise the definite integral in one variable, and I assume that you know a lot of about this. So let's suppose you have to find out the area below this curve y is equal to fx and bounded by these lines x is equal to x is equal to b and the x-axis. This bounded area, suppose you want to find this bounded area means and you usually say this the area below this curve y is equal to fx. So what do you do? Initially, I hope that you have already studied these things, so I am describing in a little brief. So initially you divide the interval a to b in subintervals by taking random points between a to b as x0, x1, x2, x3, xn minus 1 and xn. Initially we said a is equal to x0 and named b is equal to xn and all other points as x1, x2, x3, xn. Now you draw strips and try to find out the areas of each individual strip. How? So let us denote the width of strips as delta x1 is the width of first strip means x1 minus x0, delta x2 as width of second strip x2 minus x1, and so on by nth width of the nth strip as delta xn, and let fx1, fx2, fxn denote the average height of the curve in first, second, third and nth intervals respectively. Why I have taken the average height? So let me clarify. Suppose you take any strip, suppose you take this strip x1 and x2. So the curve is like this. If you take the height, this is the height fx1 and this is the height fx2. Suppose you consider the area fx1 into x2 minus x1. What this area is? This area is this one that I have marked in red. This area, you get this area. Alternatively, if you take fx2 into x2 minus x1, then what area you find? Then you find this area, this area. So you can understand that if you take the value of fx at the initial point of the interval, the area is too small. If you take the value of fx at final point of the interval fx2, the area is too much. If you take an average value of fx, then it will lie somewhere like this. So now the area of the rectangle, and if I say this average value, and here for understanding I name it zeta, so f zeta is average value. So now you will get the this rectangle, area of this rectangle. So you can see that I have marked in green. It is actually, it should be visible to you. So area of this rectangle, you can see that the area of rectangle is higher by this amount from the area bounded by the curve and less by this amount from the area bounded by the curve. So this higher amount and this less amount will try to adjust each other and the area will be precisely accurate than the areas if you take x0 or x1 or x2. So this is why I have taken average height of the curve between the interval. So now if you have got the point, so by taking average height fxk of an interval xk xk minus 1, what does this give? Area of the strip xk minus xk minus 1 means if you take uh, x fx fx naught means average height between x1 and x naught, then the area of the first strip. So do you think this area is exact? This is not exact, I have already told in figure. So now let us define a sum. Sn is equal to summation j is equal to 1 to infinity fxj delta xj. So what is this? We have already discussed that this fxk into delta xk are the average areas of any kth strip. So if we are taking this sum means we are summing the areas of all the individual strips. So does this sum forms the overall area bounded by this curve? Answer is no, because average area of any strip is not exactly the area bounded by the curve in that strip. So what we do? We do we take infinitely many number of intervals. So let us increase the number of intervals indefinitely. Means if the width of the intervals are tending to 0, then what can we get? Do you think that in this case this sum will always converge? Means this sum will always be a finite value, give a finite value? No. If you take infinite number of intervals, then in some cases this sum divided defined by this sn, this sum may give some finite value, and in some cases this sum may not give some finite value. So if this sum gives some finite value, then we say that limit n tends to infinity and this infinite sum exists, and we say it the s is the value of the sum. So in this case means if this sum is finite and we denote it by s, this s is said to be the integral a to b fx dx. So this is what you precisely already learned and what we have discussed. This is how we find the area below a curve. So this is what we do for a function of one variables. And now we will try on the basis of same thing, we will try to understand the multiple integral. So let us start defining the multiple integral. Suppose you have to find the area bounded by these two curves, y is equal to f1x and y is equal to f2x. Then in general what you do, because we have already discussed the area bounded by a curve, so we will find this area first by the same method, because you already know that method. So what you do is that you find the area bounded by the curve y is equal to f1x, means area below the curve y is equal to f1x from a to b, and you find is by this integral, a1 is equal to integral a to b f1x dx. Then you find the area bounded by the next integral f2x, area bounded below the curve f2x, and you find by this formula a2 is equal to integral a to b f2x dx. Then what you do, you subtract the larger smaller area from the larger one. Means you do this, you subtract this area in orange color from the area in blue color. So you get this area in green color, and what you can write mathematically is that a is equal to a1 minus a2. So the two integrals are being subtracted in this manner as you can see here, and finally as a combination you can write integral a to b f1x minus f2x dx. So this is how you calculate the area bounded between two curves. And now we will define multiple integral to find the same. Now we will find the area of the same region as we have done in the last example with earlier integrals of one variable, definite integrals of one variable. So we will find the same area. You can see this figure, but here we will adopt some different strategy. So what is that? Let us consider a very small rectangle in the enclosed area, and I have shown the small rectangle in enlarged form as width is dx and height is dy. So now this is what? The rectangle has the area dx into dy. Now consider an integral. Consider an integral Sx given by integral f1x to f2x dy. What is this? This is exactly f2x minus f1x, and this is exactly the vertical distance between two curves at any point. So if we consider sx into dx, this is what? This is area of the strip with width dx at a point x. Means we are taking a small width at some point x. This is, suppose this is point x, so corresponding to this point, this is the point on the curve. So we are taking this width. So if we consider Sx means f2x minus f1x, so this is the this height between these two curves, and if we multiply this height with the small, infinitesimally small width dx, then this is the area of this strip. So let us see. This is the strip. This is the strip I have marked. But what is the beauty of this method is that if you take any x, if you take any x, suppose I have marked another strip as in yellow color. So if you take this strip, so length will be this one. Length means distance between two curves will be this one. So sx will be that marked in the yellow strip, and if you take any other point, this will be this one. So we will find the elementary strip areas if we consider this sx means integral from f1 to f2 dy. Now we have find the area of one strip, and in the earlier method also we found the area of one strip. Now if with the earlier method, this is the area of one strip, so with the earlier method what does it? That integral n is equal to 1 to infinity as xn and dxn. If this exists, this should be some integral. So this, if this exists with the earlier method, you know that if this exists, we will say it a to b as x dx. So if this integral, if this sum exists, this sum is denoted by this integral, means this integral exists. And now put the value of sx here. So this will be a to b, and remember that this is value of x from a to b. So x from a to b, and sx is already f1x. This is y is equal to f1x to f2x dy, and then dx. This is the value of sx. So this is the double integral. Now we obtained a double integral. So if we write precisely, then area is equal to integral x is equal to a to b, and y is equal to f1x to f2x dy dx. This is the formula of area and this is called double integral. You can see we did not use the subtraction of integral here, but if you can remind in the earlier method we got something like this. Area is equal to integral a to b fx2 minus fx1 dx, and what we just obtained is also integral a to b f1x2 f2x dy dx. So just integrate the interior part, just integrate it and you will get the same thing. This is equal to integral a to b fx2 minus fx1 this and dx. So both are the same thing, but instead of defining two different areas and finding them, we directly find the area with the double integral. So area bounded by the curve, area bounded by two curves y is equal to f1x, y is equal to f2x is precisely the integral, double integral, integral f1x to f2x dy and a to b dx. This is the area and absolute, we take absolute value because we do not know here that f1 is higher or f2 is higher. So this is the area. In general practice means when you are doing some question, you know f1 and f2, so you know which one is higher, which one gives greater value and which one gives lower value. So function with lower value is kept with lower limit and function with higher value is kept with higher limit. Means if you have curve like this is f1 and this is f2, then f2 is below, f1 is above, so you will keep f2 below and f1 above, means f2 in lower limit and f1 in our upper limit. So this is how we do limits, and this formula depicts how we find the area in double integral. So this is called the double integral. And one more thing that you must know is that in double integrals there is a convention of ordering. Ordering means a to b, c to d, fxy dx dy. So there are two integrals, one is the area integral here you can see, and this is also an area integral, but limits are constant. So if limits are constant, we perform the integral limit according to the order. Means inner limit, inner order, inner integral is c to d, so this limit is of x, and outer integral is a to b, so this is limit of y. So when integrals have constant limit, the order follows, and when there is a variable limit, then there need not be order following thing. But you can see that this limit is a function of x, so obviously this is limit of y. If limit is function of x, this is limit of y. If limit is function of y, this is limit of x. So now we will do a question to strengthen our knowledge. So we should do this question. Find the area enclosed between the curve y is equal to x square and x is equal to y square. So the very first thing that you should do is that find the points of intersection of these two curves. So x is equal to y square and y is equal to x square. So this means x square means x to the power 4, means it gives you x to the power 4 minus x is equal to 0, and that means x and x cube minus 1 is equal to 0, and this implies x is equal to 0 and x is equal to 1. So when x is equal to 0, you can infer from any of the curves that y also equal to 0, and when x is equal to 1, y also equal to 1, means the curves intersect at 0 0 and 1 1. So means the area bounded by these two curves lies between 0 0 and 1 1. Now we will draw the curve. So this is the curve that you should draw. Here you can see y is equal to x square. This is a parabola, and x is equal to y square. This is a parabola, and I have shown clearly that area bounded by these two curves lies between 0 0 and 1 1. So now we should find the area by the method we have discussed. So area is equal to, remember, we have used constant value of x. So x will be taken from minimum to maximum. Minimum value and maximum value. So what is minimum and maximum value of x? This is 0 to 1. Now take the second integral. Second integral means value of the second integral will be taken as the vertical strip shows, means value of y will be here. So this is value of x. So once we have taken constant value of x, and again I am revising, constant value is taken from minimum to maximum. So minimum is 0 and maximum is 1 on x-axis. So we have taken x is equal to 0 to 1. Now we need the limit of y. So limit of y will be taken as lower curve and upper curve. So lower curve will give the value of lower limit of y, and upper curve will give the value of upper limit of y. So from the lower curve y is equal to x square, y is equal to x square, and from the upper curve y is equal to square root of x. You can see that this x is equal to y square will give y is equal to plus minus root x, but minus root x will lie on the fourth quadrant. So in first quadrant y is equal to plus root x should be taken. Now we have to put the limit and dy dx. This is our integral. So as I already told that this will be integrated first. Variable integral with the variable limit will be always integrated first. Integral, I am repeating, integral with the variable limit will be integrated first. So just evaluate the integral with variable limit. What is that? Dy. So this is 0 to 1 y, and limit of y is x square to root x, and put dx as it is. So this will become 0 to 1 x minus x square this dx, and you can now integrate it. This will be 3 by 2 x to the power 3 by 2, sorry, this will be 2 by 3. So 2 by 3, 2 by 3 x to the power 3 by 2 minus x to the power 3 by 3, and the limit is 0 to 1. So you got 2 by 3 minus 1 by 3 is equal to 1 by 3. So this is the area of bounded by these two curves, and we have evaluated. So as a summary, double integrals are of two types. Number one, we have integrals of the form a to b, c to d, fxy dx dy. Here we will take the limits as the order of integrals, means c to d will be limit of x and a to b will be limit of y, and in this form you can integrate any variable with respect to any variable first and any with second. Means you can integrate first with respect to x, then with respect to y, or you can integrate first with y then with x. And the second type is that integral a to b integral f1x f2x phi xy dx dy. Here we do not take limits in the order of integrals. If the integrals have the variable limit as f1 and f2, so f limits are in terms of x, so obviously this is limit of y. So this is limit of y, and this will be integrated first. Integral with variable limit will be evaluated first. Means first we will perform integration with respect to y, and then we will perform integration with respect to x. So once we have defined the limit for y, automatically the remaining limit is for x. But here in the first one you can integrate with respect to any variable first. Any variable you can integrate first with respect to x and first with respect to y. Limits are predefined in the order. In the same fashion, we defined higher order integrals, means multiple integrals. So if we have three integrals a, b, c, d, e, f, and a function, this is called triple integral. And because all the limits are constant, so limits will follow the order. This interior limit stands for x, this middle limit stands for y, and this outer limit stands for z. Again, if the variable limits occur, the limits will be taken as we discuss here. Suppose we have the limit of a to b integral f1 xy, f2 xy, and phi1 xy z, phi2 x y z. Sorry, this should be x only, this should be x only, and this should be y and z only. So we write it. Suppose we have the integral of this form, this and xy and dx dy dz. So you should understand and should remember that this integral, inner integral, this integral has the limit in x and y both. So this is the limit of z, x and y both. So this is the limit of z, so this is the limit of z. So we will integrate z with respect to z first. Integrate with respect to z first, then the limits are in x. So this, because we have integrated z, so now only dx dy means xy are the remaining thing. So this is limit in x, so this will be limit of y. So then integrate with respect to y, and finally integrate with respect to x. So this is how we evaluate the multiple integrals. We have defined the double integral, and we also did a question. We found the area enclosed between two given curve by the method described here, and then we defined triple integral. And we will do a lot of questions in subsequent lecture series. In order to avoid the length of the lecture, I am giving a stop at this point, and stay connected to find examples on double and triple integral, surface integral, volume integral, and center of gravity, center of mass. These all will be related in subsequent lectures. Thank you.